Start करें. Good afternoon, everyone. I welcome you all again. So now we are going to start this afternoon session. देखिए किसी की पीठ रह गई है.
ये छोड़ के गया होगा.
अभी पता लग जाएगा. ये जगह है दिखा रहा हूँ आपको. चश्मों की ज़रूरत सबको पड़ेगी, रोशनी की ज़रूरत सबको पड़ेगी. हम लोग उस उम्र में पहुँच चुके हैं. ठीक है.
ये आप
ज्वाइन करिए. ज्वाइन विद कंप्यूटर इससे ले लीजिए.
Recording in progress.
लेकिन हम सोच रहे हैं रोक दें. अब किससे मुखातिब होंगे? ऑनलाइन वालों से सर. ये लोग भी तो अंदर आ जाएं.
मेरा ये रीड नहीं कर रहा है. क्या बात है?
आ गया. एक मिनट बैक करिए. दिस पीसी पे आइए. आ गया.
क्यों नहीं खुल रहा? स्लो है क्या ये? क्यों? ओके.
सब देखिए.
ये इसमें वो नहीं है क्या? पीडीएफ नहीं है, एक्रोबैट नहीं है क्या इसमें?
पता नहीं कौन सा इनका रीडर है. है ना सर? ये जो थोड़ा आपसे रिक्वेस्ट करेंगे
जी.
ये जो प्रोटीनियस है के ना है इनकी क्लास है. 1 घंटा आगे खर्चा करने क्या उनको पहले करवा दें? अगर आप इसे कर लेते हैं जैसा चाहिए. ठीक है. हाथ जोड़ कर रिक्वेस्ट कर रहा हूँ.
नहीं नहीं नहीं, आप जैसा
बस आप एक नजर देख लीजिए पीडीएफ में क्योंकि ये हमारे टॉपिक कुछ चीजें आई नहीं है नीचे की बॉटम वाली बिना डिलीट कर सकते हैं. पीडीएफ आप देखेंगे वो ज्यादा बेहतर है.
Professor Kulkushan.
Yes, Professor Kekena. We are just trying if we can manage and we can arrange your talk first. Wait, can you wait for 5 minutes? Professor Kekena.
Okay, Professor. Okay, Professor, wait.
Okay. Yes, you just wait for 5 minutes. I'm extremely sorry because there was already some 20-30 minutes delayed in the program from the beginning. That's why we are lacking of time. But now I can understand you also have other engagements. So just wait for a minute, 5 minutes. Professor Kekena, I'm just waiting for some other delegates also to come and sit in this conference room so that they can listen you also. Just give me some 5 minutes.
Okay, Professor. Am I the host now? I can share my screen? Meanwhile.
And also I am making you host so that you can have the control. You can mute if you got disturbance from any other presenter. or any other participant. Okay?
Okay, Professor.
Yes, Professor Melissa Kekena, you are here with us. That's our pleasure. And I'm showing this gratitude that you have accepted our invitation to give a talk in this conference. So let's start your presentation.
Okay. Can you just confirm, Professor, if you can see my screen that side, the one that I've shared?
It is quite visible. We can see it.
Okay, thank you. Thank you very much. Okay, so what I'm going to talk about today is the numerical investigation of this brasselator chemical model by what they call residual function using mathematical software. This is I would say a numerical work. It involves numerical approximation, a lot of numerical things that are going to be explaining, okay? So, first, is it? Okay, so my presentation outline is as follows. I'm going to talk about the abstract, give a little bit of introduction, show the general brasselator model, and also define what I'm speaking about, what they call residual function, the numerical integration method which we used called the Gauss Quadrature, and also the graphical results together with the tabular results. Okay. Okay, so in my presentation, a mathematical framework of checking accuracy for building algorithm by means of residual function is developed and investigated. So we took the brasselator model as a case study on building algorithm from mathematical software. So the algorithm that we use include implicit ring-a-coda with different order, atoms, and backward differential formula. So the graphical results are shown on an interval from 0 to 30. So the keywords that you must take care of is the brasselator model, the mathematical software, implicit ring-a-coda with different orders, a residual function, and what refer as the working precision. So I'll explain what do I mean about the working precision. Maybe some of you who have used the mathematical, you will be familiar with the working precision. Okay. So this presentation will outline the importance of checking accuracy of built-in algorithmics from mathematical software. Because one of the problems is that researchers tend to neglect checking accuracy of those built-in algorithms from the mathematical software. We all know that most of the nonlinear systems, such as the brasselator, Lorentz systems, their analytical solutions doesn't exist. So what researchers tend to use, the researchers tend to use built-in algorithm to simulate the numerical results. So one of the things that they tend to not to do is to investigate how accurate are those solvers that are embedded within particular mathematical software. So this defined residual function will be will be derived by integrating the Brasalator system and collecting all the terms to one side. And what we'll do is that the decimal logarithmic of modulus for the residual function will be plotted on an interval from 0 to 30. That is the little bit of introduction that I'm going to do. So our model is just a Brasalator. We have done the Lorentz system. We also managed to publish a paper where we simulated the work using the Lorentz system. So the second part, which is what one of our students is working on, is the Brasalator chemical model. Okay, so this is a classical Brasalator model, which is a system of first order differential equation with some nonlinearity terms, where all those constant K1 until K4 are all positive and A and B are all positive. So this is our initial condition. You're having your X naught there and the Y naught for those particular system. So what we normally do is that we're going to integrate this system 1. So if we integrate this system 1, like we integrate this right hand side, we're normally going to have X of t minus X naught. So that right hand side, we're just going to have an integral there. Integral from 0 to t. So where tau is just a dummy variable. Tau here, what we introduce tau there is just a dummy variable. So what we've done, we've collected all the other to one side. So we've collected all this term to one side. So which is equation 2 and 3 for both those ones from that particular system there, system 1. So what do we do? We're going to define a residual function for each and every, for equation 2, and also define the residual function for equation 3, which you can easily see that is defined from that equation 4, which is just a representation of a res t, and this one is a residual for the y function there. So what we do, we're also going to do the summation of the 2, which will then be the residual for the system there, for that Brasalator model. So the summation, this equation 6 is just the sum of the 2 residual, res x, or residual x, and residual y. Why are we doing this? The whole idea is that we have these built-in algorithms that are embedded in Mathematica. So we want to check which one is the most accurate when to use for this particular model, because you can pick a built-in function without checking the accuracy. It's going to give you the solution, but we wanted to how accurate is that particular solver, considering that we're looking at this particular model. So these are classical initial conditions that are there from this particular system. That there are in a lot of literature reviews, you're going to get this particular constant, and also the value of b there is 201 over 100, and so the a value is a 1, where your initial condition of x naught is a 0, where the y naught is x naught is a 1, and y naught is a 0 there. So what we do is that from that particular equation, if you look at from equation 4 and 5, we're going to put those particular constants in the K1, K2, K3, and K4, and also A and B there. So if you look at this one, this is now the new defined for the residual X, and also the defined for the residual Y there. And this equation 9 represents the total residual, the summation of those two functions. And this particular integral term, you see the integral from 0 to t of this particular terms here. Actually, let me just talk of this one from equation 9. This particular term, together this particular one, we're going to use Gauss Quadrature, the 3 points Gauss Quadrature, to numerically investigate that. Because even on Mathematica, there is a built-in function that uses Gauss Quadrature. So you can just call that particular function to numerically approximate this particular definite integral there, because this is just a simple definite integral. Okay. So this is just an explanation of the Gauss Quadrature, where you're given the particular function f of x on an interval from 0 to t, from a to b, with these distinct points, x1, x2, x3. So this definite integral can be approximated as a summation from 1 to 3 wi f of xi, where wi are those quadrature weights and xi are the quadrature points. So this is, we all know from classical numerical methods that we normally use, these are well-known formulas for approximation in this kind of definite integral. So as I've just indicated, these integrals here, we're going to be using Gauss Quadrature to numerically approximate them.